Now let's examine this configuration. This is a system configuration in the sense at some instance of time a system is having these many processes A, B, C, D, E, and a system is having the process 5 processes, and these are all the resources it has. So one resource is tape drivers, and other resource is plotter, scanner, CD-ROM, and anytime I think these tape drives and then plotters and scanners, they are not actually used these days, but I taken it from the textbook, so don't worry, just you can think of them as some ordinary resources. You might not have seen those resources recently, but then scanners you might have seen it, plotters and then tape drivers you might not have seen them. Assume that there are some kind of resources and then CD-ROMs, right? So the system is having 4 resources and then 5 processes, and the resources are assigned to the systems like this, a process like this. For process A, 3 tape drives are assigned, 1 scanner is assigned, and 1 CD-ROM is assigned. So this matrix will show you how many resources are assigned to each process, right? That is what is given. And second thing is this matrix is going to show you resources still needed, which means after assigning these many resources to this process, how many resources are still required by the process to finish their execution, which means see this, A has taken 3 tape drivers, 1 scanner and 1 CD-ROM, and now A is still asking for 1 tape driver and 1 plotter more in order to finish its execution. That is what is the meaning of it. Okay, and along with that they have given us these 3 vectors. One more thing, various authors, they follow various conventions, so don't stick on to one particular convention, which means depending on the question, in the question paper, whenever they give the questions, they'll clearly mention what does each matrix represent and what does each vector represent. Vector means the array, right? What does each vector represent and what does each matrix represent. They are going to clearly specify what is the meaning of each one. So depending on the question, follow their terminology. Don't stick on or by heart this terminology. Okay, so now in this terminology, this author is saying this. Now he has given a vector E, and E means the total number of resources available, right? So E vector is representing how many total resources are available in the system, which means the first one is like this. So how many resources are there? 1, 2, 3, 4, right? The first one represents tape drivers, plotters, scanners and CD-ROM. It means that in the system totally we have 6 instances of tape drivers, 3 instances of plotters, 4 instances of scanners and 2 instances of CD-ROM. And then P and A. So P and A represent similarly the same thing, right? So P is how many processes are assigned, how many resources are assigned currently. See this? If you see the tape drivers, 3 plus 2, which is 5 are already assigned to the process. Therefore these are P represents how many are already process or under processing, which means how many are already given to the process. So 5, 3, 2, 2. How can you derive this? You can even just add them and derive this. These two can be generated, which means if they give the total number of resources available, right, you can derive how many resources have been allocated to the process till now just by adding these columns. It is 5 here, it is 3 here, it is 2 here and 2 here, right? 5, 3, 2, 2. And next thing is you can find out how many are available now. So how to find out how many are available? These are the total number of instances which are present in the system, and these are the number of instances which are allocated to the process. Therefore if you subtract from this one, if you subtract this, you will find out how many are still available and how many could be allocated to the process, right? Now this is also called as a state. State means how many processes are there and how many resources are there and how many resources are currently being allocated and how many resources are required more, right? This entire thing is called as state. Now a state is said to be safe, right? I'm talking about safe. A state is said to be safe if there is a sequence in which you could satisfy the need, right? If you could satisfy the need of this process in some order, right, then that state is said to be safe. Now let's examine if this particular state is safe or not. This is going to be safe if we can satisfy the requirements of all this process in some order, so that everyone will finish their execution. I mean, everyone will take all the resources and finish their executions and come out, right, without getting involved in deadlock. Now watch this one. Now availability is 1020, isn't it? Availability is 1020. Now with this 1020, can you satisfy any of the needs? Can you satisfy 1100? Not possible, because the number of tape drivers required by A is 1, but then you have 0, right? See, sorry, the plotters required by A is 1, but then you have 0, therefore you cannot satisfy the need of A. Clearly it is like this: need of A is 1100, but the available is 1020, therefore this particular need cannot be satisfied by this availability, so you cannot think about satisfying A first, so don't satisfy the need. Now let's see if you could satisfy the need of B. So B is saying 0112, can you satisfy it? 0112. It cannot be satisfied clearly. Why? Because this particular value cannot be satisfied, as well as this cannot be satisfied, even though this can be satisfied. Therefore don't do that. And now what about C? C is 3100. Yes, it too cannot be satisfied. These two cannot be satisfied, right? And what about D? D is 0010, right? Yes, it can be satisfied clearly. So D is asking for only one scanner, and I have two scanners, and if I allocate this whatever D is asking, if I allocate it, then it will run to completion and it will release whatever is already present with D. Okay, one more thing: whenever you satisfy the need of a process, it will take all the resources that you are giving it, and then it will run to completion and it will release everything that you have given and it was holding, which means earlier it was holding some resources, right? What are the resources it was holding? 1001. So it is going to release this as well as the process which you have assigned. So watch this: if you are able to satisfy, or if you are satisfying the need of D, right, then what happens is, after you satisfy this need, then D will run to completion, right, and then D will release all the resources which it is already holding, along with the resources which you have given it. Now how many resources are you going to give it? Only this one, right, which means 0010 you are going to give it. Fine. And now it is going to take this, and already it has got 1101. Therefore after giving it, it will become 1111 and it will run to completion and it will release all the resources, right? What are the resources it will release? 1101 it will release. Therefore I am just writing like this: whenever I could satisfy the need of a process, I am just assuming that it is going to run till completion, and I'll just take the allocated resources allocated vector and I'll add it to the availability. See, this is the available vector, right? Now if I allocate the need for D, D will run to completion and it will release all the resources allocated, which means D will release 1101. Therefore new available will be 12121. See, generally people will get confused here. Already it needs 0010, and now it is holding 1101. Then you are saying that you have given it 0010, then it is even supposed to release that 0010 also, right, along with this. Yes, that is what is happening, that is what is there. Even though I am actually saying that I allocated it available, I didn't change anything, which means I am not actually giving it, I am just assuming that I have given it, and therefore it is going to release everything. This point is very crucial, and I don't think that you'll understand it easily. Those who didn't understand it, I'm just repeating it, watch it. What I mean to say is, yes, I am providing D with what it needs, and then I'm assuming that D has completed its execution, and therefore whatever it was holding, it is releasing. Therefore all these resources will be added to the pool of available resources. You need not add that, because that is already included in the availability of the earlier vector. Got it? So earlier it is there, already 1020 is there. Now I have satisfied the need, and therefore it is releasing everything, and only those resources will now get added. You need not add that one. Got it? Therefore this one will be new available vector, right? So what did you satisfy here? D is satisfied completely, right? And now the new available vector is 2121. Fine. Now with this new availability, now check what could be satisfied. Already D is satisfied, you need not worry about it. Now with this 2121, can you satisfy A? Yes, A can clearly be satisfied, right? Therefore, I am going to satisfy the need of A. If I satisfy the need of A, which means I'll take one from here and one from here, and I'll give it to this, and again it will give me back that one and one. Therefore, this remains same, right? I need not change it. As well as it will even release whatever were the resources it was holding earlier, right? So what are the resources? 3011. This will be released. Therefore, now the new availability will become 5132. This is the new availability, right? And one more thing, see, when I have the availability as 2121, it is not just A's request I could satisfy, I could have even satisfied E's request also. Therefore, you could either picked up A or E, that doesn't matter, right? The order in which you pick up the process doesn't matter as long as you are able to finish all the process, right? Let's see. Now the new availability has become 5132. Fine. Now with this new availability, say A is done and then D is done. What are the requests that you could satisfy? Clearly B could be satisfied, as well as C could be satisfied, as well as E could be satisfied, right? Here itself we can stop and say that every need can be satisfied, but let's do this. Now let me say I am going to satisfy B's need. If I satisfy B's need, which means from these available resources, if I allocate whatever it needs, anyway it is going to return it back, right? Return whatever I gave it back, right? See, 112, 112, which means from here if I take out 1, here if I take out 1, and here if I take out 2 and give it to B, anyway it is going to return me back. Therefore I have to add it, so I am not going to add this. I am just assuming that it is going to run to completion and it is going to release the already assigned resources. So what are the already assigned resources? 0100. Therefore now the new available becomes 5232. This is new availability, right? So now using this new availability, 5232, what could be satisfied? See, B is over. You could easily satisfy C. So if I try to satisfy C, now if I satisfy the need of C, it will release, what will C release? C. C's need can be satisfied because it needs only 3100. I have 5233. Therefore it can be satisfied. What will it release? 1110. Therefore C is going to release 1110. Then what will be new availability? 6342. This is new availability, right? Now C can be satisfied. Therefore finally using 6342, I can satisfy the need of the final process, which is E, right? Then what is E going to release? Oh, E doesn't need anything, right? Therefore E doesn't need anything at the first place, right? So completely we got 6342. Now check it. Completely, how many ever resources were available at the beginning? They are all now become available because all the process have released them. Now what does it mean? From this state, when you are in this state, you could give the resources you could assign to the process in some order. What is the order in which you assign here? The order is D, A, B, C, E, right? So you could assign the resources in this order: D, A, B, C, E. In fact, E is not required, but still, right? You could run them in this order in such a way that D, A, O. Actually, E needs 2110. E is not holding anything. I forgot it. I did something wrong there. Actually, E is not holding anything, but E needs 2111. Therefore, I am going to assign it 2110, and then it is going to give me back. That is why I am not adding anything. I am going to assign it whatever it needs, and therefore it is anyway going to release them later. Therefore, I am not going to subtract from here. I'll make the available stay like that, and then I'll try to add whatever it was holding earlier. Since it was not holding anything, I am just adding 0, right? So now watch it. So now this is the order in which I have satisfied the needs of all the processes: D, A, B, C, E, right? So from a state, if you could find out some order in which all the process needs can be satisfied, then such a state is called as safe state. What is safe state? If you could find out some order in which you could satisfy the needs of all the processes in some way, right, without getting, then that state is called as safe state. Safe state. So safe state means you are able to find out a state, a sequence in which you could satisfy without having any deadlock. Therefore this one is safe. Now let's do one more example here. Let us assume that first at this instance of time, this is the requirement and we have assigned it, and suddenly see, even though the process need these many resources, they might not ask you for these many resources at the same time. They will just ask you, few resources first. I mean, at any time any process can request you for some few resources. Now assume that when you are in this state, suddenly B is asking for let's say B is asking for 0 1 0 0, which means even though B needs a total of 0 1 1 2, right now it is making a request for this. It is requesting you to assign or give it one plotter, right? Or maybe instead of taking a plotter, let's say scanner. Let us say B is asking for 0 0 1 0, right? Because anyway this is not available, right? So now watch it. This is the state, and now operating system has got a new request from B in such a way that it is asking us to give it 0 0 1 0, which means it is asking for one scanner right now, even though it requires 0 1 1 2 in total to finish its execution. Right now it is not asking for everything, right? Right now it is asking for only one resource, right, which is 0 0 1 0. Now what will operating system do is, operating system will act as if I assign this if I allocate this resource to B, will the system be safe? In case if the system is going to be safe even after allocating this resource, then we shall allocate it, right? So the process, see, what I'm trying to say is, this is the state, and now B, we got a new request from B. Then what will operating system do is, it will act as if it has already allocated the resource to the B. It doesn't allocate it. It will act as if it has already allocated it to the B, and then it will find out whether the resulting state is going to be safe or not. In case if the resulting state is going to be safe, then it will do the actual allocation. Otherwise it will not allocate it. It will just roll back, right? Now assume that operating system is going to act as if it has allocated this one. So if this one has been allocated to B, then what will be the B's matrix? B's matrix will look like this. This is resource assigned. Then how does it look like? Here it is going to get 1 instead of 0, and then in future need, it doesn't need 1, which means this one will become 0, right? And here the process assigned will become here 3, isn't it? Check this. Now the scanners have become 3 assigned, and now the availability will become 1. The reason is total availability is 4 and assigned is 3, therefore now the availability will be 1. These are the total number of resources in the system, and now 3 are already allocated, therefore 1 will be available now, right? Okay, so now our new availability has become this one, 0 1 0 0 0. Now this is the state resulting after B has been allocated the request. What is it? 0 0 1 0. We didn't allocate it yet, but we are acting as if we allocated, and now we shall find out whether this state, resulting state, is safe or not. In case if it is safe, then only we are going to allocate it, otherwise we are not going to allocate. Let's see whether it is safe or not. Now what is new availability? The new availability has become 1 0 1 0, right? Now using this availability, can I satisfy any of the needs? Just check it. Can I satisfy A need? No, because A needs 1 1 0 0, it cannot be satisfied. Can I satisfy B? No. Can I satisfy C? No. Can I satisfy D? Yes, D can be satisfied again. So let me satisfy D. So what does D need? D just needs 0 0 1 0, and as I have all this, D needs just 0 0 1 0, and as I am capable of giving it 0 0 1 0 because I have 1 0 1 0, right? And now I am going to once I allocate D whatever it requires, then I assume that D will release whatever it is already holding. Therefore what is it holding? 1 1 0 1, therefore it is going to release it 1 1 0 1. Then what will be new availability? 2 1 1 1, right? Now I am going to take this as new availability, which is 2 1 1 1, right? and using this availability, can I satisfy anything? D is already satisfied, right? Now in the remaining, can I satisfy anything? A can be easily satisfied. Therefore, if I satisfy the need of A, which is 1100, then what will A release? A will release 3011, right? Then what is it? Now the new availability will become 5122, right? So now the new availability is 5122, right? And so A is satisfied, and next one that has to be satisfied is B. I mean, that could be satisfied, isn't it? 0102 is easily satisfiable. Therefore, if I satisfy B, what will B release? B will release 000110. I hope you understood this. Why am I adding only this? Because from this I already allocated this one. See, from the available resources I already allocated the need, and anyway they are going to submit them back. Therefore, I am not going to subtract it from here and then again add that one which is allocated. I am just going to leave it like that, and assuming that whatever it was holding earlier, it is going to leave it. So fine, B is going to release this. Then what will be new available now? 5 2. I am just adding it. 3 2. And now the new availability is 5 2 3 2, right? And then B is satisfied, A is satisfied, and then let C can be satisfied. C requires only 3100, and I have 5232, right? Therefore, if I release all the resources that C is holding, what is C holding? 1110, then what do I get? Then the new availability will be 6342, right? Then the new availability is now this. So with the new availability, E can be satisfied, right? So new availability is 6342, and E needs only 2111, therefore 2110, it can be satisfied, but then E is not holding anything, therefore nothing will get added. So finally the new available will become 6342. Got it? So now watch it. So now this state is also safe, because after allocating the resource to B, still I am able to allocate the resources to all the remaining process in some order, in such a way that there is no deadlock. Therefore, even this state is safe. So whenever operating system sees that a request, whenever any allocation is going to lead us to a safe state, operating system is going to allocate it, right? So now you can assume here that operating system will definitely allocate it, and therefore this resulting state is also safe. Now let's see one more example, which means in this state, from this state, right, original state was safe, and later after allocating the B request, we got the state to be safe, and let us say in this state again I'll make one more allocation, and the new request is, let us assume that E is requesting us for one more scanner, which means E is requesting us 0010. It can request us because its total need is 2110. This is the total need of E, but right now it just wants one resource 0010, which is nothing but scanner. Now what happens if I try to assign it? Now I don't know whether to assign it or not. Then what I do is that as operating system, I'll try to assign it. I'll act as if I assigned it, and then I'll analyze and see if the resulting state is safe. In case if the resulting state is safe, I'll assign it, otherwise I don't, right? Now assume that I am going to assign it. Then if I try to assign it, then what do I get here? 0010, right? And that is assigned. Therefore the future need is going to decrease once I assign it. And what about the availability? It will become 0. And what about the allocated processes? It becomes 4, right? And now check this. 4 minus 4 is 0, 6 minus 5 is 1, 3 minus 3 is 0, 4 minus, that is how, right? And now watch it. So now the new availability has become 1000. Using this, I'll try to see if I could satisfy any need. Can I satisfy the need of A? Not possible. Can I satisfy need of B? Not possible. Need of C? Not possible. Need of D? Even D is also now not possible, because D requires 0010. Earlier D satisfying D need was possible. Can I satisfy E need? Even satisfying E need also not possible. Therefore, you cannot satisfy the need of any process, so it is definitely going to lead to deadlock. So assigning this request to E, what is the request made by E? 0010, assigning this request to E, granting this request to E, is going to take us to a state which is unsafe. Unsafe means we are not able to find out any sequence in which we could satisfy the need of all the process. Therefore, that is called unsafe. Safe means if you are able to find out a sequence in which you can satisfy the need of all the stations, all the process, then that is safe. But then here it turned out to be unsafe. Therefore, what can you say? We are not able to find a sequence in which we could satisfy the needs. Therefore, the system is now unsafe, right? So from this, what you could understand is a operating system is going to see if a state is unsafe or not, safe or not. If it is safe, it will make the allocation. If it is unsafe, it will not make the allocation. And one more thing is, whenever you have some available available vector, and if the available is not even able to satisfy the least of the needs, what is the minimum of all this? The minimum of all this is D, 0, 0, 1, 0, right? And if you are not able to satisfy even the minimum of the needs, then definitely there will be a deadlock. Therefore, the necessary condition for in order to have no deadlock is the current available. Using this, you should be able to satisfy at least one process. We have already seen it. I think that xi yi problem, gate 2006 problem, I guess, xi yi yp yq and then xp xq, there we have seen it. The total availability was then xp x plus xq, right? If you have already seen that problem, if you didn't see the problem, leave it. But the total availability there was xp plus xq, and using that xp plus xq, you should be able to satisfy the resource of need of at least one process, which is nothing but the minimum need. If you are not able to do that, then definitely there is a deadlock. If you are able to do that, maybe there might not be a deadlock, but we are not sure, right? So using this, we are not able to even satisfy one need. Anyway, it is nothing but the unsafe state. So this request will not be granted, right? So why? Because it is unsafe, right? Therefore, this request will not be granted and it will be delayed further, which means right now it will not give it. It will just say that you can ask me later on. Availability and then assign, right? And again it will restore the system back to the safe state. So whenever any request is whenever we get any request, before granting it, check that this granting will lead us to a safe state, then only you grant it. Otherwise, leave it and just go back to the safe state. Got it? And then delay the request. Fine. Now whatever I explained you, right, this is called as deadlock avoidance algorithm or Bankers algorithm. So what Bankers algorithm will do is, whenever we get any request, it will find out whether the allocation or granting the resources is going to lead us to a safe state. In case if it doesn't lead us to a safe state, it will not grant it, right? In case if it leads us to the safe state, it will grant it. That is nothing but the Bankers algorithm, right? So we shall see some problems on the Bankers algorithm, and this method is nothing but deadlock avoidance. Avoidance means we try to avoid it. We don't prevent it. There is a chance of deadlock, but then we never get into deadlock at all. That is called Bankers algorithm, and this method was proposed by Dijkstra again, right? Semaphores and then this method, both are proposed by Dijkstra only. So this is a popular method using which we can avoid the deadlocks. Let's see some more examples on this and then the algorithm.